The next topic in motion is something called displacement and velocity. So we've already discussed distance, which is basically how far an object moves during some time interval. It's called a scalar quantity. So in physics, there's two types of quantities that we can describe. Scalar quantities have magnitude only, meaning how much, what is their size, and that's distance, right? So we could talk about our trip, to the beach or whatever. It's 100 miles away, and that's our distance covered. That's what we would read on our odometer, for example, when we take our trip. Displacement is a little bit different than distance. And so displacement is how far an object travels, but it only measures along a straight line path, and it's the distance specifically from the start to the finish, and it's directed just along a straight line path. So obviously, if we took a trip to the beach and it was 100 miles away, we didn't travel in a straight line. So we would have to find the displacement, we would have to take out a map and actually look at the starting point, look at the ending point, and just basically draw a line from the start to the finish, and then measure what that distance would be. So displacement is called a vector quantity, and vectors in physics tell us not only how much or what the size is, but also what direction that particular quantity is pointing. So displacement is a vector quantity. It has both size, so how far if we're talking about our trip to the beach, but also in what direction did we travel. So in this particular picture, we have another representation of an object at different time intervals, or equal time intervals of 1 second that goes by. And so if we were starting off at the 4-meter mark, that's our initial position, and then our final position would be at the 12-meter mark. We could ask, what is the displacement? And so we're going to focus on one-dimensional motion. So we're going to look at displacement along the horizontal direction, similar to previous examples. And so we have our x-axis with our origin over here. And in one dimension, we can basically represent the displacement as being positive or negative. And it's based on the direction of the motion. So how did I move? Did I move along my coordinate system so that I'm moving away from the origin? Or am I moving in the negative direction? So in general, we can represent the displacement as delta x, and it is the difference between the final position and the initial position. So again, over here, my initial position is at 4 meters, and my final position is at 12 meters. So I can draw a line, a straight line, from my initial position to my final position, and that represents the direction of the displacement along that straight line path. So this is obviously pointing along the positive direction on the axis, and I can determine what the displacement is by taking my final position of 12 and subtracting my initial position of 4 meters, and I get my displacement is 8 meters. And it turns out to be a positive number because my displacement is along the positive x-axis. This picture looks almost identical to the previous picture, except you'll notice that my initial position is at 12 meters and my final position is at 4 meters. So my displacement is just a vector quantity, or the line that points from the initial position to my final position. So this is pointing in the opposite direction, right? It's pointing towards the origin, or it's pointing along the negative direction, right? Positive direction would be along the axis going, to the right, and this is going to the left. When I calculate my displacement, which is the final position minus my initial position, my final position is at 4 meters, my initial position is at 12, and I end up getting a negative 8 meters. So in both of these cases, the distance covered is the same. Both of these displacements cover the same distance of 8 meters, but the direction is different. In the first case, it was the direction was to the right. In the second case, the direction is to the left. So that means that displacement is not the same, because displacement is not only how far, but it's also in what direction, and they do have different directions. So that's a big thing about displacement that's different than distance covered. So we can ask a couple of questions about displacement versus distance. And so the first question is it possible for the amount of displacement to be different than the distance covered? And the answer to that is yes. So here's an example where maybe I'm in a race and I have a start over here for the race, and then the race takes some path. And then here's the finish line over there, and so this line represents the distance that was covered. The displacement, however, is just a line that starts at the start, ends at the finish, and the displacement would be the distance from the start to the finish along a line connecting the start to the finish. So my displacement, this line, is definitely shorter than this distance covered over here. Now obviously this is a two-dimensional picture and we're considering just one dimension, but the idea still works the same way here, that it's possible that the displacement is different than the distance covered. Obviously, if you went along a straight line path and just walked from the start to the finish, then the displacement would be the same as the distance covered. Is it possible for the object to cover some distance and have zero displacement? And the answer to that question is also yes. And that a case for that would be if you start and end at the same point. So maybe you're in a race and you go around a track and you end up back where you started. You obviously cover some distance, but your displacement is zero because you ended up exactly back where you started. So there is a difference between distance and displacement, and we have to make sure that we think about that as we're looking at examples and if we don't use them interchangeably. So we've talked about average speed. Average speed was just the distance covered over the time interval. And now we're going to define something called the average velocity. And so the average velocity basically measures the displacement covered in a certain amount of time, which of course is different than the distance covered. So average velocity is a vector quantity. It has both size and direction. So the average velocity is going to tell you how fast, but also in what direction you're moving. So we define average velocity as displacement divided by time. If we're talking about one-dimensional motion, which is what we're going to focus on right now, then we would write the average velocity, and the symbol that we use for that is a v. Our displacement is just, we said, is the delta x, which is the difference between my final position and my initial position, and then over the time interval, delta t. So normally we assume we start off at time t equal to 0, and that we measure it at some later time t. So we can write this as the average velocity is just the difference in my position, final versus initial, over the time interval. So again with the units that we would use, the standard units for physics are meters per second. But we can certainly have other units, anything that's length over time, kilometers per hour, feet per second, centimeters per second. I didn't put miles per hour on here, but that would also be an example of a unit that we can use. We will always try to focus on using meters per second. When we talk about average velocity, direction does matter. So the average velocity can be positive or negative depending on the direction that the object is moving. So remember in the previous example, the displacement in one case was positive, and in the other case the displacement was negative. So if we were to look at those displacements over time intervals, the velocity, the average velocity, would be positive in one case and it would be negative in another case. So it's telling us what direction the object is actually moving. So in general, we will use directions in terms of left, right, and up, down. So our positive direction along the horizontal will be to the right, and a negative direction will be to the left. If we look at the vertical direction, positive direction will be up, and negative direction will be down. So this is just a standard Cartesian XY coordinate system where, if we draw a coordinate system here, the X direction would be to the right, which would be positive, and the Y direction would be upward, which would also be positive. So let's consider some examples. So here we have another example of an object that represents so the dots represent where the object is each second that goes by. So over here the time is at the top and then the position is at the bottom. So after 1 second the object is at 1 meter, after 2 seconds the object is at 4 meters, after 3 seconds 9 meters, and so on. So the first thing we could ask is the object moving at a constant speed? And we should be able to look at this picture and look at the dots and realize that those dots are not equally spaced. And so in order for an object to be moving at a constant speed, it has to cover the same distance in equal time intervals. And each of these intervals are equal time intervals and the distance is not the same. So the answer is, of course, that the speed is not constant in this case. So we're going to answer two questions. We're going to determine what is the average velocity, not speed. We're going to now measure the average velocity in the time interval between 1 second and 2 seconds, and the average velocity between 2 and 3 seconds. And we're going to see how do those average velocities compare over those 1 second time intervals. So let's start with the 1 second to 2 second time interval. So here's my 1 second and here's my 2 second. So my displacement is just going to be the distance between where I start and where I end up, pointing along the line connecting those two. And so I realize that my displacement here, I end up at 2 seconds at 4 meters. I started off at 1 second at 1 meter, so my displacement is going to be 3 meters. But in general, I can write down average velocity as my final position minus my initial position over my time. At 2 seconds, I'm at 4 meters. At 1 second, I'm at 1 meter. And the time interval between 1 second and 2 seconds is 1 second. So my average velocity is 3 meters per second. So between 1 second and 2 seconds, my average velocity is 3 meters per second. I can go through the same process between a time of 2 seconds and a time of 3 seconds, and I realize that my displacement is now larger, right? It's a bigger line here, and so my average velocity would be my final position minus my initial position over my time. At 3 seconds, I'm at 9 meters. At 2 seconds, I'm at 4 meters, and then the difference in the time there between 3 and 2 is 1 second, so this is 5 meters per second. So over the interval between 1 second and 2 seconds, the average velocity was 3 meters per second. Now over the next interval of time, it's 5 meters per second. So the speed of this particular object is not constant. So here's my picture again below, and we're going to answer a few questions. So in the previous example, is the velocity constant? And of course the answer to that is no. Did you have to make a calculation to see this, or could we have used the figure? And I sort of already answered this question, but I did not have to make a calculation. I could look at this picture with the dots, which represent the object in equal time intervals, and realize that the distance covered every second that goes by is actually getting bigger. It's not constant, and that means that the object is not traveling at a constant speed. So the object covers a different distance each second. We could ask, what would the graphical representation look like? And so here's what a graph would look like when the velocity is not constant. So I start off at time t equal to 0 at 0 seconds. After 1 second, I'm at 1 meter. After 2 seconds, I'm at 4 meters. After 3 seconds, I'm at 9 meters. 4 seconds, I'm at 16 meters, and then I actually put another one here which didn't fit on my picture. But if I kept this up after 5 seconds, I would be at 25 meters. So one of the things that I can look at here is I can look at over equal time intervals, what does the rise over the run look like? What does the slope seem to look like? So I can put these steps in, right? So over the first 1 second interval, I cover a distance of 1 meter, right? So you can hardly see that on the graph there, but there's 1 meter. Between 1 second and 2 seconds, I cover 3 meters. So there's my rise right there, should be 3 meters. Between 2 seconds and 3 seconds, so between 2 and 3, the distance covered, or the displacement, is 5, right? So there's my step there is 5. Over the next 1 second interval here, so the horizontal axis is my time, I cover a distance between 16 and 9, so 7 meters. And then I could do the last one, which I don't have on my picture, but it looks like this. So what's happening is when I make a graph of the position of this object's motion versus time, and the object is speeding up, what's happening is that the slope, or the rise over the run, so these are equal intervals of time, and these rises right here are getting bigger and bigger. And each one of these rises represents the distance, or the displacement, covered over these time intervals between each of these 1 second time intervals. So the slope of this graph is increasing. The rise over the run is getting bigger and bigger over these time intervals. So the slope of the position versus time graph is getting steeper over time, which means the speed is increasing, or in this particular case we could say the velocity is increasing. So the position versus time, or knowing something about what the position looks like over time for an object, is going to tell us a lot about the motion. It's going to tell us where the object is. It's going to tell us something about the displacement that's covered. But more specifically, it's also going to tell us, is the object traveling at a constant speed? Is it speeding up? Is it slowing down? And so the fact that this slope is getting steeper, making these equal time intervals and then the steps, and it will tell us that the velocity is getting bigger. So this is a nice way to see slope increasing, is looking at distances between points, equally spaced time intervals, and looking at what that step looks like.